official.
All right. Okay, so what about you guys? Did you guys understand everything all right, or did you guys have some questions too?
I feel like I'm in the same boat. I was kind of like, well, first of all, I didn't really understand it.
Yeah.
I was like, oh, okay, this makes sense. And now I'm kind of like, so why would I want to? I mean, I don't know. I kind of thought about it and came up with some reasons in my head, but I don't know if I completely understand it. So why I'd
Right.
want to do it or what the, you know.
And I feel like when I do get it, I just have to not think about it so much. But then when I really try and get it, like I
can hear you now.
myself. Yeah, I hear you. We
Okay,
hear
cool. I'm like, what is going on?
you. um, for example, I'll read you guys something and then I'll explain why I don't really get it. So in the video, at the very end of the second video, he goes over some key points, and one of them is the very last one says the standard deviation of the distribution of sample means equals the standard deviation of the parent population divided by the square root of the sample size. So like I understand how to do that, but like what does that mean? Like for example, I think they gave us a hold on, let me find you guys. I think they gave us like a problem where they said like the average hours that BYU students study is like I don't know 10 hours, and then it said the standard deviation is I don't know maybe 2 or something, and like I get that you would do the standard and then it said that there was a sample size of 100 people. So to find the standard deviation thing, it'd be 2 over the square root of 100 or whatever, right? But what is that? Like what? I don't know.
What's the point? Yeah.
Yeah, like what?
It seems like so much work.
Yeah, I'm just having a hard time understanding like what's the I guess the use and really what like it means. Like I can do it, but I don't get that.
The point of it, yeah.
Yeah, I don't know. And like, did you guys look at the little applet this time where it showed the graph and then it would show like it would have a sample of like 5 and then it would take the average of those 5 and then did you guys see that or?
Yeah, I saw it. It kind of confused me at first more than helped, but then like after I went back and like read the text, then it made more sense as to what it was doing.
Yeah.
Right.
It kind of made things more confusing for me.
Right, because I mean, I don't want to confuse you guys, but like my thoughts are okay, how do I even explain this? Okay, so if you have a sample of a population of say 10, you have a sample size of 10, and then you're gonna, and then when it asks you for the mean, if I understand it correctly, you're taking the mean of all the possible means,
right?
Like, but if you have a sample of 10, how are there more than one mean? Because it's just 10, period. Like, why is it like is it saying like if you were to have a sample of 10 of these 10 students and then a sample of those 10 students and a sample of those 10 students over there, and then you compare the averages of each of those 10?
But it's not really saying that. It's just saying
right.
the mean. It's not saying there's multiple groups. What's the mean in each group? Yeah, that's weird.
Yeah, see, it never says any of that stuff that I just said. However, how is there, you know?
That's what it's doing.
Right. So I don't know. It was frustrating. Yeah. And then I did the homework and I got a C on it and like so I'm kind of like I don't know. I'm just a little frustrated with this lesson. So I'm just trying to wrap my head on it.
Yeah. Okay, maybe I don't know if this is right either because I didn't entirely understand this, at least not as well as the other ones. But
right.
what I do understand, like what I've kind of pieced together, I guess I feel like I understand it now. I'm just not entirely sure if what I understand is correct.
Right. It makes sense in your mind at least, right? So.
Yeah, it makes sense in my mind, but I don't know if it's at all right.
Yeah.
So kind of just to like reiterate, I guess what you were saying is that basically what we're doing is taking a mean of different means.
Okay.
And so that's like the whole process, right? I mean, really simplified, is that we're taking the average of averages.
Okay.
And so the way that like that works in general, and it kind of made it sound like you can imagine that if the three of us, right, we went and did the same study, and so we're like, you know, going and collecting the same type of data, but we all go and collect data from different samples, or even the same sample, but the three of us go and collect it, right? Then we're probably going to get slightly different numbers, right?
Right.
And so my mean is probably going to be different from your mean, which is going to be different from, you know, Jason's mean or whoever's. And then if we took those means and plotted and found the mean of them, then we find a more true mean, I guess, because we're taking the average of the averages.
Right.
And so that's kind of the idea of like having it be separated. And then it kind of takes it a step further where it's like, well, instead of doing it on, you know, 3 different populations, what if we just took the population and then only chose a subset of them, found the mean of that, chose a subset of another piece, found the mean of that, chose a subset of another piece. By subset, I mean like just a part of it. So only like 10 of the 100 and then 10 of the 100 like you were saying.
Right.
So we take those means and find an average of them, which the reason that that's helpful is because if we're taking the mean of means, then we're always going to get a normal distribution.
Okay.
Because if that kind of makes sense, because you can kind of visualize like a right skew graph where it like goes up and then has the long tail, right?
Yeah.
Well, that's not a normal distribution, but if we took sections of it and took the averages, then the graph of the averages would be a normal distribution, and then we can do statistical analysis stuff on it.
Okay.
And so it's basically a way of taking a non-normal distribution and turning it into a normal distribution, so that, or an approximately normal distribution, so that we can then do all of our z-index stuff and the things that we've been learning about on non-normal data.
Right.
Okay. I don't know if that's at all right, but that's kind of what I put together.
It makes sense, though.
Yeah.
And so that's kind of the way I thought of it, is that it's kind of like, you know, multiple people going out and collecting the same data. They might get different actual values, but the data
should be similar.
Yeah, should be similar. And then if you take the average of it, that's when you get that normal curve, is because they're all getting the same data. It doesn't matter if it's left or right skewed or wonky or whatever. If we take the means, then obviously there's going to be a true mean, between all 3 of us, but then somebody's probably going to be on the left and somebody's going to be on the right of it, and so you're going to get a normal distribution.
Got it. Okay.
Makes sense.
Yeah, that makes a lot more sense to me.
But that's, I don't know.
I guess what it comes down to is the questions. When they ask you the questions, it doesn't come across to me that they're asking how you explained it, but how you explained it seems to be, you know, how you would get the correct answer, if that makes sense. So. Yeah. So I guess basing it off of how you explained it, it makes sense. So.
Seems like they're using a lot more math lingo than is needed to begin with here. That's what's so confusing. You're like, what's the
that almost confuses you. You know?
Yeah.
I didn't know forever like what I understood like the whole sampling. They always talked about the sample, and I'm like, well, which sample? What are you talking about? And they're talking about like the sample of the means, I guess, from the other samples. Anyway, this is kind of confusing as to what they're actually talking about.
Yeah, I'm hoping the next few lessons kind of go back to the easier stuff.
Yeah. But, add all these up and divide it by the number.
Yeah, I like that.
I'm hoping that the next like 6 lessons are more gospel oriented. Because that's what my last class, D212, like the first like 6 or 7 weeks was really, really like numbers, graphs, standard deviation, all kinds of spreadsheets. And then like the second half of the semester was more like, it honestly was really more gospel oriented. It was like, hey, here's a scenario, and then answer the questions based off of that. And so it was a lot funner.
That's funny.
Keep your fingers crossed.
Yeah, there's always hope for that.
And if you're listening, teacher, please give us some help.
All right.
One
Any
thing
other questions?
I was kind of confused on like the central limit theorem and what that, like, I kind of understand it in general, where if the sample size is big, obviously, then the mean becomes more normally distributed. I mean, I think kind of what I just explained is the central limit theorem.
Yeah.
Because there's the law of large numbers, which just says the bigger the sample size, then the standard deviation from the mean should get smaller. And so the more people you ask, then the less random your data is going to be. But
yeah, what is it, the central limit theorem? What's it called again?
The central limit theorem.
Yeah. I just understand it at that basic level. I mean, I don't think I can really worry about learning it any more than that right now.
Yeah.
I don't know.
You're like, I think I know what answer to check.
Yeah.
I mean, isn't it basically, if you have a large, a large pool, right, of a whole bunch of random variables, isn't it just saying that it's going to be pretty normally distributed? Isn't that all it's saying? I guess that's how I understand it. You're going to have with a whole bunch of random independent variables, given that, you're going to have a pretty well-rounded distribution curve. That's how I understood it. Maybe that's totally wrong, but
no, I think that's right. I think it's kind of like what we just explained, where if you take it doesn't matter the actual curve of the population itself, but if you take the sample mean of the population, so you take those sections, then you're going to get a normally distributed curve if the sample size is large enough.
Right.
Okay. All right, I'm good. I think I kind of understand it. I don't know.
Yeah. Hopefully for the test we can, all three of us can get by, So.
Yeah.
Well, we seem to have done so far this year, so that's good.
Yeah.
All right, so I haven't read, so should I read this week?
Sure. Yeah, that sounds good. So this is lesson 6, group meeting?
Lesson 6, group meeting.
Okay, let me open this up. Okay, cool.
All right, so number 3. When taking samples, are you guys all there?
Yeah. Mm-hmm.
When taking samples of n equals 5, what was the shape of the distribution of means histogram when the parent population is right skewed?
All right.
Well, since it's a small, oh wow, my computer's.
You're going crazy there.
Yeah, seriously. If it doesn't work, just hang up and call back, and then it seems to solve it.
Is he just frozen?
I don't know. I think so.
Huh.
I bet he can't even hear us. I bet you we can say a whole bunch of mean stuff about him, and he probably would have no idea. He's cool. Yeah, he was doing that to me earlier, and I don't know what happened, so I just hung up and called back, and it was fine then once I called back. All right, so when taking the samples of n equals 5, what was the shape of the distribution of means histogram when the parent population is right skewed? Right skewed, normal, left skewed.
Oh, okay. So here it says for this course, if n is greater than or equal to 30, we will say that the distribution of the sample means will be approximately normal. So
Greater than 30. So if it's less than 30, so it wouldn't be normal then because it's not greater than.
it's still going to be right skewed because your means aren't large enough, right? This is saying if we take our data set and put it into take the chunks, and each chunk has 5 things in it, right? Then if we take the average of that, it's probably not going to do well. Sorry, no, this is saying if we have 5 samples.
Yeah, and you're saying if it's greater than 30, it would be normal, correct?
Yeah, approximately normal. So number 4 should be normal. Because even if it's right skewed, it should be normal.
Right.
And then 5 and 6 are all going to be normal too, because it's saying basically the same thing, but it says if the parent population is normally distributed. Well, if it's normally distributed, we know that the whatever it's called, the distribution of means histogram is going to be normally distributed as well.
Even if n equals. Oh, okay, because it's normally distributed. So
yeah.
That seems weird that they would have that both be normal, though. Okay.
Hey guys, sorry, my computer just turned off on me. I don't know. Where are you guys at?
We're on number 3 still.
Oh, okay, that's good. So what are you guys thinking? Would it be skewed right because it's such a small sample, or I don't know.
Yeah, that's what, we were just reading in the book, and it says for this course, if n is greater than or equal to 30, we will say that the distribution of the sample means that it's approximately normal. And so basically saying, yeah, since the sample size is smaller, that means it's probably going to look pretty similar to what the parent population was.
Okay.
So it should be right.
Yeah, that's what I'd go to.
Because it's not going to be normal, and I don't know why it would go skewed left all of a sudden.
Yeah. So.
All right. So 3 is skewed right. 4 we put normal for 4.
Normal. Oh, because it's such a big one, huh?
It's such a big one, so it's greater than 30, right?
Yeah,
and then 5, Bryce, you think that's normal as well, even though n equals.
Yeah, it'd be normal because the parent population is normal, right?
It's normally, yeah, because that's normal.
So if you take the average of a normal distributed population, then hopefully the results would also be a normal distributed population.
Right.
Gotcha. Okay.
So 5 is normal. 6, when taking samples of n equals 100, what was the shape of this distribution of means histogram when the parent population is normally distributed?
I think normal, right?
And we're also saying, yeah, normal for that one as well.
Okay. Cool.
All right. Number 7. When would the distribution of means be normally distributed? Choose all the correct responses. The data are drawn from a population that is normally distributed as the sample size is small.
Yeah.
That would apply.
Yeah.
Data are shown for a population that is normally distributed and the sample size is large. That would apply because it's normally distributed.
Yep.
Data are drawn from the population that is right skewed and the sample size is small. I would say that would not be.
Right.
And then data are drawn from a population that is right skewed and the sample size is large. And based off our answers, that would be checked as well, right?
Yep. Mm-hmm.
Yep. Basically the same questions.
Yeah, exactly.
Yeah. That worked out.
Beautiful. All right, which of the following, number 8, which of the following gives the best explanation of the central limit theorem?
Oh, no.
I know, right?
If the parent population from which the data are drawn is normally distributed, then the sample mean, is that X?
That just means the average, right?
Will follow a normal distribution.
I think it might be that one.
I know. I think it might be too. Let's check that and just read the other ones. It doesn't talk about a bell-shaped at all in the definition that I saw. So from bell-shaped data approximately 68, that's not it.
No, that one's wrong.
It's a really nice try, but that's not it. Yeah. If the sample size is large, the sample mean will be close to the population mean.
That's the other theorem.
Yeah, that's the law of large numbers, right?
Yeah.
And the last one is the sample size is large, the shape of the sampling distribution of the sample mean will approximately be normal. That one could be it too.
Yeah, I don't know. I mean, based off what I know from
I think it's the first one.
You think so? Okay.
I think so. I mean, if we get it wrong, I guess it's my fault. But what do you think, Bryce? First or last?
I'm still processing.
Yeah, because I mean, according to the reading and stuff, I think both of them are in that, you know. But I think this is where it comes down to like technically like what I don't know, whatever the theorem really is.
Well, you know what? I don't know that it really talks about if the parent population. It talks about a large sample size, right? If you have a large sample size, the shape of the sampling distribution of the sample mean will approximately, even though I actually think that's probably the better answer. Because I don't remember it talking about a parent, right? It didn't talk about a parent population.
Yeah, I'd probably say the last one, just because the first one's kind of like
more like the question.
The last one is the actual useful one. But the first one's basically saying if you put in a normal distribution, you'll get a normal distribution out. Whereas the last one's saying if you put in a skewed distribution and you do this thing, then you'll get an approximate normal distribution out. And so it's like that one's actually doing something.
Okay, let's go for that one.
And I guess I feel like the first one relates more to the previous questions than really the central limit theorem. You know what I mean?
Yeah.
So, okay, I'm good with that.
Okay, so the last one it is.
The last one it is. Number 9, let x be random variable with population, and population standard deviation is 6. Suppose a sample size is n equals 36 is drawn from this population. What is the mean of the distribution of sample means?
It's just 10, right?
Yeah, it should just be 10.
Yeah.
That's all my knowledge about that. It's just the same.
Yeah.
Same as the mean they give you, I think.
Okay, so then what would the standard deviation be then?
I think it would be you do 6 over the square root of 36, or 1, which is 6.
Isn't that 1?
It's 1, yeah.
Yeah.
Then it says 3 decimal places, so do 1.000.
1.00. Yeah.
I mean, I guess. It's not a comma, so we should be okay. So.
Okay. All right, number 11. Regardless of the distribution of population, if the sample size is n, which is greater than 30, is it greater or less than? Oh, holy crap, I can't remember.
Greater than 30.
Greater
than 30, right?
Mm-hmm.
What's that?
Oh, nothing. Go ahead. I was just saying, it says it's large and we want it to be big.
Right. What would the shape distribution of the sample mean? What the shape distribution of the sample mean?
So it's saying if the sample size is larger than 30, what would the shape be? So it's normal, because 30.
It'd be normal.
Yeah.
Anything greater than
And but see, then 12 says what theorem would justify your response, and I think it's the central limit theorem, right? Or no?
I think so too.
But then doesn't that one go along with? Well, I guess that's how we answered number 8. So I guess that's good, right?
Yeah.
So
it kind of seems like the central limit theorem uses the law of large numbers in essence, but the law of large numbers says nothing about the shape of a distribution curve.
Right.
Right. So 12, I think, is central limit theorem, right?
Yeah,
Yeah, I think
I think
so.
so.
Okay.
So number 11 is normal. Number 12 is central limit theorem.
And for 10, you guys wrote 1.000?
Yeah, 3
Correct.
zeros after the decimal.
Okay. All right.
Yep.
Ready?
Try it.
Yep.
1, 2, 3. 100.
Hey.
Nice. There we go.
Good job, guys.
There we go. I needed that.
I hate that. Are you sure you want to do this?
It's like, wait, do I want to do this?
No, I don't think I want to.
Am I sure?
Did I miss something?
Oh, okay. While I got you guys on the phone, Thursday, is there any way to do the class at 4? I guess, sorry. My time was 5. You guys are 6.
It's 6:30 for
right?
us. Yeah.
Okay. Is there any way that we could do the call at I guess 5 your time, 4 my time?
5 my time. That works for me. I could do it.
Yeah, I think I'm okay too.
Okay. The kids, they have my kindergartner is in a play, and I want to say it starts at 4:45. So if we can get we could do it at 4 o'clock, that'd be great. So
Yeah, that's fine by me.
allow me to get there.
Okay. So 5 our time, 4 your time.
Correct. Yeah, 5 your time. Whoa,
Cool.
Got it.
Whoa.
Cool.
All right.
Thanks, guys. I'm off for my 10-mile run. See ya.
All right.
Nice.
Have fun with that.
See you
Can't
later.
wait.
Yeah.
All right. See you guys.
Bye.
Bye.